Properties of crystals. These are real-life examples of vitamins and other proteins and drugs that we use, like, for example, insulin and vitamin B12 are in there. Scientists spend a lot of time and energy in getting these structures and seeing what they actually look like. And the reason why is that it's the arrangement of molecules in the crystal that give it its chemical properties. So if they can modify and control these chemical structures of these known drugs, well, they can make new drugs, new vaccines, new medicines. In other words, right, big bucks. I was speaking to an X-ray crystallographer, and he said this was the hardest part, is identifying and getting a really nice crystal to work on. But once he's got it, he said he's good to go. Diamond and graphite. What's the difference? Well, they're both made of the same element. What's that? Carbon. It's their crystalline structure that's different. For example, if we take a look at diamond, here's its structure. Very compact. It's tetrahedral in shape. If we take a look at graphite, how are its carbon atoms arranged? See how they're essentially planes. So one plane can just slough off the other. It can be slippery, and graphite is a solid lubricant. So that's why it works in your pencil, because just one layer just sloughs right off the other layer. Over here we have some salt and some sugar, right? I mean, the crystalline structure looks pretty much the same. But what types of compounds are they? Well, salt, right, consists of ions, so it's an ionic compound, right? And sugar consists of molecules, so it's a molecular compound. So let's take a look at this. We have these different types of crystalline structures, and the stronger they're held together, right, they'll have increasing bond strength, right? So if they're held together more strongly, they'll have a higher melting point. So out of these different solids, the solid with the highest melting point are the covalent network solids, like diamond, right? They're held together by covalent bonds, right? And consist of nonmetallic atoms. An ionic solid, so that's the next strongest type of crystal. It's held together by not covalent bonds, ionic bonds, right? And consists of ions. Here's an animation.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
So it's a simple plus minus of the ions that holds it together. Metallic solids, the third highest melting point, they're held together by, well, kind of the answers right here, the electron C model. So you have all these cations in this crystalline structure, and in between them is the sea of electrons. It consists of metallic atoms. Okay, electron C model.
Bonding in metals is described by the electron C model. Solid metals behave as if constructed of a repeating pattern of metallic cations, surrounded by delocalized electrons. These electrons are free to move among the many cations in the crystal. This model explains the relatively high electrical and thermal conductivity of metals. When deformed, no bonds are actually broken. Instead, cation planes slip past one another, leading to the metallic properties of ductility and malleability.
So molecular solids are held together by intermolecular forces, right? The forces that exist between molecules and consists of molecules. So this is an important table because if you can identify the type of material, right, the type of matter, you can figure out what type of crystalline structure it's going to form, and therefore predict its bond strength and melting point of that crystal. So it's a big deal. Some different types of crystalline lattice. Here's the simplest ones. We have our simple cubic unit cell. Let's take a look at it. Okay, so there's one atom at each corner of this unit cell. So a unit cell is just something that's repeating itself again and again and again, and that's what creates the crystal. So if you have an atom at each corner like this, that is the simple cubic unit cell. So there's the body-centered unit cell. Let's just go through all these, then we'll figure out how many atoms are in there. The body-centered unit cell, it looks really similar as a simple cubic, except there's an atom in the center. An entire atom in the center for body-centered. And then in face-centered, right? So we again have an atom at each corner, but there's also an atom at each face of the cube. So half of it's in the unit cell, and half of it is outside of the unit cell. So how many atoms are contained in each unit cell? Well, there's 1/8 at each corner. That goes for all of these, right? One-eighth at each corner. Right? Because 1/8 of the atom is actually inside the unit cell at each corner. Just 1/8 of it is. Right? So if you have 1/8, but there's 8 corners, that means there's just going to be one atom. Because there's just 8 corners, right? So in a body-centered, well, we'll have one atom from that. We'll have one atom from that. But then you have one in the center, so 2 atoms for body-centered. And then for face-centered, we've got 1/8 at each corner, right? So that'll be 1, plus we have 1/2 on each side, but there's 6 sides. So 1/2 times 6. So 4 total, 4 atoms. Okay, so know this. Know how many atoms are in each unit cell, because that's going to be the answer for a lot of homework questions. And you'll see that coming up. Now, it's right here. Gold has cubic crystals whose unit cell has an edge length of 407.9 picometers. So it's cubic. So each edge is that length, right? 407.9 picometers. The density of this gold is 19.3 grams of gold in every cubic centimeter. Okay, so we've got 19.3 grams of gold in every cubic centimeter. From these data and the atomic mass, calculate the number of gold atoms in a unit cell, assuming all atoms are lattice points. What type of cubic lattice does gold have? So calculate the number of gold atoms in a unit cell. What they're talking about is this, right? Are we going to get 1 atom, 2 atoms or 4 atoms? And if we get 1 atom, it's simple. 2 body-centered and 4 face-centered. Okay, these number of atoms, right? Calculate the number of gold atoms in a unit cell. That's going to, how are we going to get it? Let's get the mass of 1 unit cell. And divide that by the mass of 1 gold atom. So if we get the mass of one of these, get the mass of it, and then divide it by the mass of 1 gold atom, and we're going to get 1, 2, or 4. So how can we get the mass of 1 unit cell? Well, we know the density. Let's take the density times the volume of 1 unit cell. Right? Because, right, volume units will cancel, and we'll have grams, and then we'll just divide it by the mass of 1 gold atom. And I'll show you how to do that if you forgot. Okay, let's get this density. Let's get this top part. The mass of a unit cell. The density times the volume of 1 unit cell. So the density, they said, was 19.3 grams of gold in every cubic centimeter. Now, life is confusing here because look at this darn picometer thing. I know that there's 100 centimeters in a meter. Well, we could put that in. That might help. And we're going to have to cube it because it's cubed, right? So I'm in centimeters now. Oh, sorry, I'm in meters now because the centimeters canceled. I'm in meters. Let's rewrite this. 407.9 picometers is the same as 407.9 times 10 to the what? Meters. Pico means 10 to the negative 12. Not sure, just Google it. Okay? So let's just get things into picometers then. We need to have get things into meters. Oh, we're in meters. So let's take this times 407.9 times 10 to the negative 12 meters. We have to cube it. All right. Let's make sure our units are canceling out here. Otherwise, we're messed up. We have centimeter has to cancel out 3 times. There it is, cancel out 3 times. Meter has to cancel out 3 times, and it does. So we'll get grams of gold. $19.3 times 100, but you have to cube it, times 407.9 times 10 to the 12 negative, and that you have to cube also. So I got about 1.31 times 10 to the negative 21 grams of gold. You should get a small answer, because this is a very small little unit of gold here. A little tiny, tiny particle. Okay, so the number of atoms in our unit cell will be 1.31 times 10 to the negative 21 grams of gold divided by, okay, how do you get the mass of a single atom? Do you remember? Do a little aside here. The mass of one atom. what you did, this always works. Take the molecular weight, divide it by Avogadro. And you'll always get the answer, okay? Because molecular weight is the mass of Avogadro's number of them. So divide by Avogadro and you get the mass of one of them. So in our case here, we're going to have the molecular weight of gold. Ooh, what's the molecular weight of gold? Here's gold. 196.97. 196.97. 196.97 grams of gold. Hello, Avogadro. 6.22 times 10 to the 23rd. 196.97 divided by 6.022 times 10 to the 23rd. You get about 3.27 times 10 to the negative 22. Grams. So that's the mass of one gold atom. We'll put that on the bottom. 3.27 times 10 to the negative 22 grams of gold. Now we better get 1, 2, or 4, remember? I got 4. So it's base-centered, cubic. That is my answer. Okay, so what we did is we just pretty much found the mass of one unit cell by taking the density times the volume of one unit cell. And remember, volume of a cube is length times width times height. And then we divided what we got by the mass of one atom. You get the mass of one atom by dividing the molar mass by Avogadro. Which of the following do you expect to be molecular solids? Okay, well, not this guy. He's a metal. Not this guy. He's ionic. Well, that's a molecule. That's a molecule. So those work. All right. Molecular solids, remember, you need nonmetals. That's how you make molecules. Arrange the following compounds in order of increasing melting point. Okay, so remember how that went. We had covalent solids at the very tip of the peak there. Okay, then we have ionic solids, then metallic, then molecular. Right? So that's the order that we're going to follow. So an increasing melting point. So the bottom is molecular. Is anything in here molecular? You bet. These two are. Okay, so what holds together molecular solids? Intermolecular forces. So which one would have the weaker intermolecular forces? Because it'll be at the bottom of the pile. Well, they both have hydrogen bonding, but this one is more free, right? So I think this is going to be stronger hydrogen bonding. Look how accessible that is. Stronger hydrogen bonding. So that would put B at the bottom. And then, what is that? C. So we'll have B and then C. Now we got to pick between D and A. They're both ionic. D and A are both ionic. But look at the difference. The charge is a lot stronger with calcium oxide. So D would be next, and then A. Because those plus 2 and minus 2 charges are stronger, more strongly held together than plus 1 and minus 1 charges. Arrange the following substances in order of increasing melting point again. So again, remember we have covalent network, then we have ionic, then we have metallic, and then at the bottom of the pile was molecular. So, increasing melting point. Increasing. List them out. Bottom of the pile is molecular solids. Do we have any? Yeah, we've got two of them. We got one here and we've got one here. But this one has hydrogen bonding. This one's just dispersion. So C would be the weakest because hydrogen bonding is pretty strong, remember? Those intermolecular forces, hydrogen bonding is the strongest. So B would have a higher melting point than C. Then what's next? Oh, this one's ionic. What is this one? Covalent network. It's like diamond, now the same structure. So those covalent network ones are kind of hard to find. Just recognize them as individual nonmetals sitting there, and it's pretty much always covalent network. So we'd have D and then A.